In the last segment, we claimed that the transform of ut minus a is just e to the minus as over s. And, it seems authoritative. It's off the formula sheet, but after all, I'm the one who typed up the formula sheet. So why should you believe this? Well, the reason is that we can do this calculation ourselves to see what it's equal to. So I want the transform of ut minus a. And I know that the Laplace transform of any function f is the integral from 0 to infinity e to the minus st times the function ut minus a dt. Now, this is a pretty simple function, right? We know that ut minus a only takes on two distinct values. It's 0 if t is less than a, and it is 1 if t is more than a. So one way of thinking about this is the following. We could split this integral up. We could integrate over the interval from 0 to a, and then we could follow up by integrating from a on out to infinity. However, this first integral is extraordinarily simple. Ut minus a to the left of a is just equal to 0. So that factor is 0 there, and therefore this whole integral just drops out. So we're left with this, the integral from a to infinity, e to the minus st times 1 dt. Okay, now this looks an awful lot like the transform of 1. But the catch is you start at a rather than starting at 0. So I would like to do a change of variables here. So I want an x, and the x should be equal to 0 at this endpoint. So what we're going to do is say we'll let x be t minus a, and then of course that's equivalent to saying that t is equal to x plus a. We'll use that in just a little bit. And since these coefficients on x and t are both 1, we see that dx and dt are the same thing. So you can translate this to an integral in x. So let's do that. All right, when t is equal to a, x, well, plug in the a here, x is equal to 0. And when t goes to infinity, well, when t goes to infinity, you're subtracting off finite a, so that means that x also goes to infinity. So this is the integral from 0 to infinity, e to the minus s times t. But t is x plus a. And dx and dt are equal. So we now have an integral from 0 to infinity, just like we want for our definition of the Laplace transform, and we just have to figure out how to evaluate this. Well, it turns out not to be too difficult. Well, what you do is make the observation that you could distribute here e to the minus sx, and then you'd have minus sa. But if you are adding exponents, you could split those up and multiply with like bases. So that's just a bit of algebra there. If we multiply these together, you'd have minus sx minus sa, and that, after all, is what you have here when you distribute. Okay, now this right here, notice we're integrating on x. X is the variable. This thing right here is constant, and therefore e to that is constant, and therefore you can just put that on the outside of the integral. So this is equal to e to the minus sa times integral 0 to infinity e to the minus sx dx. And if you'd like to, for good measure, you can throw in a 1 and say, oh my goodness, look at that. That is exactly what we would write to transform the one function. It's e to the minus st times 1 dt. Well, we've all just changed the letter. That's all this is. So this is e to the minus sa times the Laplace transform of 1. And the Laplace transform of 1, well, we looked that up just a moment ago. It's equal to 1 over s. And that's such a common one, you should have it memorized if you don't already. But so this thing is 1 over s, and we have e to the minus as over s, just as advertised way back here when we computed the transform of this little single square wave here. So there is there's the derivation, and you can use that now anytime that you need it with full confidence. Now that is great if you're just transforming the unit step function all by itself. But what we would like to know is this other formula that has been that has appeared in the table. If you have ut minus a times f at t minus a, and we're going to assume now that this is an f that actually has a transform, that you get a finite integral, what is that equal to? And that's the next step in the derivation, and we'll do that one now. It turns out to be essentially the same kind of calculation. Well, this is defined to be the integral from 0 to infinity, e to the minus st, times ut minus a, f at t minus a, dt. And now the substitution really is obvious, right? The t minus a is appearing in here repeatedly. So x, we set that equal to t minus a. dx and dt are, of course, equal. Just as we argued before, when t goes to infinity, so does x. So the first step is to say, well, this thing is just equal to 0 until you get to a, so you may as well start your integration at a. And then you apply this substitution here and say, okay, we're going to switch over to x. When t is equal to a, x is equal to 0, and they both go to infinity together. And this then is f at x. That's just a 1, right? So you get this, which is nothing other than the Laplace transform of f. However, we have left a little piece undone here. This is true, but it's not done. That t should be replaced by x plus a. There we go. Now it's fully translated to the new variable x, and just like we did before, we've got e to the minus s times a comes off as a separate factor. We're left with e to the minus s x times f at x dx, and that is e to the minus, well, as and sa are the same, times the Laplace transform of f at t, or f at x, which we call cap f at s. So sure enough, this is indeed the right formula to transform ut minus a times f at t minus a, and that's the proof.